AI. That was by Dr. Kumar G of NIT Calicut. And then in the second session, Professor Anil Kumar S introduced us and took us into the world of supervised learning and basically the case of linear regression. And then he introduced the concepts of overfitting, underfitting, bias, and variance. And today he continues with more concepts of machine learning. And with all your permission, let me welcome Professor Anil Kumar S into this Google Meet. Anil sir, please take over. Thank you.
Thank you, Shiva sir. Okay, in the last session, we had a discussion about regression model, and we had discussed linear regression, polynomial regression, how we will evaluate regression models. Then we had a small discussion of what is bias, variance, underfitting, and overfitting. So today, what we are planning to do is to discuss about classification. So what are the ways in which a classification operation can be done using supervised machine learning models? That's the today's objective. So let me go to the presentation. Okay. Today, what we are planning to do is about discussing three classification models, namely logistic regression, decision trees, and support vector machines. And we'll have a small discussion on how we'll evaluate classification models. What are the performance measures indicating the performance of a classification model? That is the main topics which we included in our presentation. Now, you all know what is actually classification. So we'll be having some inputs. These inputs may belong to some discrete categories. Like the simplest one is, say we may be having the values of eosinophilia, ESR, and uric acid. And based on these values, a person can be classified into two categories. One category is a category of people who are suffering from arthritis. The other category is persons who do not have any arthritic issues. So we have two categories, arthritic and non-arthritic. So our task is we will be given some values, for the values of some uric acid values, eosinophilia values, and ESR values of a person. And our task is to actually to classify whether that concerned person is belonging to the arthritic category or in the non-arthritic category. Here, that is the categorization is the task that is involved. And the simplest task is we are having a mail, we want to categorize it into a spam or non-spam, like that. And we are having chest X-ray images, we want to classify them into, say, suffering from bronchitis or not, suffering from pneumonia or not. Those, and we can have multiple categorization also, more than two. Like we'll be given the video of a person, that is his facial expression is given, and we want to classify what is his emotion, whether he is actually a depressed mode, he is happy, he is actually in an angry mode. So in that case, we have more than two categories. Generally, our task is to categorize our inputs to separate discrete categories. And here The goal is actually we'll be given some input features, and based on these features, we want to categorize your data. And for that categorization, you are actually needed to design a function that will map these features to the corresponding classes. This is the objective. And the basic classification models, which involve actually logistic regression model, decision tree model, support vector machine model, and neural network model. And out of these four, I will not be discussing neural networks model because that itself is having is too detailed. It takes more than 2-3 FDPs to explain the neural networks in detail. See, even up to the deep learning, so we take more than 5-6 days to explain in full detail. So I will not be covering these neural networks. So I will be covering the first three models in this session. So it is a session objective where we will be discussing the basics of logistic regression, decision trees, and support vector machines, and how these models will be implemented in Python. And as in the previous session, we'll be experimenting with some Python codes, and we'll be measuring the models using our performance measures. And these programs are actually given to you, and the data set is also given to you. You may experiment this in your Google Colab platform. However, I'll be running this code, and if you want, you can also have this. Now, let me first discuss about what is logistic regression. See, I told regression is actually a kind of prediction, predicting some continuous value. That's actually regression. But logistic regression, it is actually a model for classification. So there's a little bit of confusion there. See, on one side, I'm telling that it's predicting, or it is actually doing prediction, some kind of prediction, and on the other side, I'm telling that it's used for classification. So there is a logic behind logistic regression. So you may think that a regression, say a classification model, it will take some features like eosinophilia, ESR, and uric acid values. Then it will output class labels. One that is arthritic, other non-arthritic. That is our normal intuition. But in a logistic regression model, what it will do is that it is used for only binary classification. That is the first thing. So we have two classes actually. Class 0, I call them as class 0 and class 1. So every input actually is supposed to belong in one of these categories, class 0 or class 1. So instead of outputting the class label as your data is in class 0 or class 1, what the logistic regression model will do is that it will give you a probability value. It will give you a probability that what is that value? That value will be giving the probability that your input is belonging to class 1. What is the probability that your input is belonging to class 1? That probability is given to you. For example, that probability is 0.8. Then what is the conclusion? There is an 80% chance that your input is in class 1. And accordingly, there is only 20% chance that the input is in class 0. So, and after that, we will be using some threshold to classify. That is, if the probability is greater than some 0.5, then we classify it as class 1. If the value is less than 0.5, then we classify it as class 0. So in fact, the logistic regression model is not giving the class label asset, but it's only giving you the probability that your given input is belonging to class. So that's the key idea that is used here. Instead of predicting the continuous value, it predicts a value between 0 and 1. And what is that value? That value is the probability that your y or output is equal to, or class is equal to 1, given the features x1 to xn. Here also you will be given. Here x1 is actually the uric acid value, x2 may be the eosinophilia value, and x3 may be the ESR value. There are three features, and accordingly your y is arthritic. 1 means arthritic, 0 means not arthritic. One example. And see, you may wonder why such a function. I have written a function called sigmoid function. A probability that y is 1, given the features x1 to xn. See, in logistic regression model, this probability is calculated using, say, such a complex formula, 1 by 1 plus e power minus alpha 0 plus alpha 1 x1 plus alpha 2, etc. See, you may wonder why I have not taken the probability as alpha 0 plus alpha 1. See, why I am not taking probability of y equal to 1 as alpha 0 plus alpha 1 x1 plus alpha 2 x2 plus like that. Why I am not taking as alpha 0 plus alpha 1 x1 plus alpha 2 x1 square plus alpha, like we have done in polynomial regression and linear regression. So there is an intricate there's some intricacies actually involved there, and I actually want to explain that later. After discussing all these slides, I'll try to explain why this relation actually came into picture, and this function where is called 1 by 1 plus e power minus x, that is called the sigmoid function. So when you are actually giving the inputs x1, x2, x3, etc., xn, so these x1, x2, x3, etc. values are actually substituted there, and you will find the probability. And if the probability is normally greater than 0.5, then that particular input is categorized as class 1, and if it is less than 0.5, categorized as 0, class 0. Then you may ask, what is alpha 0, alpha 1, alpha 2, etc. These are the parameters that are to be computed based on your training data. So you will be given a training data which has maybe some 100 samples. Say, discussing actually 100, each sample corresponds to one person's data. That is eosinophilia value, ESR value, then uric acid value, and also will be given the exact output also, that whether he is an arthritic person, whether he belongs to arthritic category or not. So we will be given a labeled or input output pair data, and using this data, you actually want to find out these parameters alpha 1, alpha 2, etc., alpha n. And that's actually what is meant by designing a logistic regression model. And after computing this alpha 0 to alpha n, later it can be used for, say, those data for which we don't have any output known. That's the objective of designing a logistic regression model. And the function 1 by 1 plus e power minus x, it's called a sigmoid function. It's a very, very important function as far as machine learning is concerned, and it is highly used in neural networks also as some function called activation function, and that you will see in the later sessions. And let's see what is the nature of the sigmoid function. This is a sigmoid function. Say I have plotted x along the this x-axis and the value 1 by 1 plus e power minus x along the y-axis, and you see that that function is always ranging in the interval 0 to 1, and beyond, say, actually some 0.8, it is actually converging to 1, and beyond some minus values, and see below some minus values are converging to 0, and it is supposed to meet at 0 when the input is actually infinity, and supposed to meet at 1 when the input is actually supposed to meet at 0 when the input is minus infinity, and supposed to meet at infinity when the supposed to meet at 0.1 when the input is infinity. And this is a curve, and so you can see this is just kind of S. You can see the letter S that is rotated through an angle of 45 degree. You can, if you see in that direction, you can see you can view it as a kind of the English letter, that is capital S, actually is in a rotated fashion. This function is called the sigmoid functions, and people will also call it as a logistic function. I'll explain why that is called. And what are the features of this model? Say, it is actually a very, very good model which has several strengths. The thing is that the most important feature of this is it is actually very, very easy to train, and it will be, see, if you actually train a logistic regression model comparative to other models, it will take less time, and even for data sets with too many features and too many samples, we will be able to complete the training as early as possible. And when the data are linearly separable, when the features are linearly separable, that means the data are linearly separable means. So let us see, I already explained actually this is used for only binary classification. So you take a data set which consists of data with or inputs with for class 0 and inputs for class 1. And you plot these data on a coordinate system. So for example, in a 3-dimensional or a 2-dimensional system, so you have only one feature and you have only two features. You have only two features and you are plotting them on the 2-dimensional. And what I can see is that the class 0 inputs and the class 1 inputs I can separate by means of a line. So that means on one side of the line, all the class 0 inputs data will be lying, and on the other side, the class 1 out inputs will be lying. In such a situation, we say that our data or features are linearly separable. And in that cases, this is actually performing very well. And this is actually considered as one of its advantages, at the same time disadvantage. And in most of the practical situations, we cannot say that our features are actually having some linear boundary. So in that case, this is not good. It is not giving some correct results. So that's about logistic regression. I'll come later why we will be using logistic for. Let me say, as in the previous class, let me go to the implementation of logistic regression. And here today I'll be using a data set called the PIMA data set. Actually, that's a diabetic prediction data set. It's a data set that is available in Kaggle, and it is one of the most famous data sets that are normally used by people to teach machine learning, especially for classification models. And what is this data set means? It consists of 8 input features, and based on that, it's actually categorizing whether a particular person is actually a diabetic person or not. That's a thing. So we have only two categories: diabetic and non-diabetic. That's all. And based on these 8 features, so we have X1, X2, X3, X4, X5, X6, X7, and X8 here. And we are going to the discussion. We are actually coming across the discussion of how this model, logistic regression model, can be suited for performing classification for the PIMA dataset. Okay. So in the first code segment, I have given an implementation for logistic regression for this PIMA dataset. If you want, you can have a look at this PIMA dataset. PIMA dataset actually is given to you, shared with you. It consists of 8 features. Totally 9 columns are there in your dataset. So the features are actually pregnant, then some pressure value, skin test, mass. So many age, class, so many features are given to it, and actually there are 8 features. So I don't know whether all these features are actually contributing to the prediction of contributing to the categorization of whether a person is diabetic or not, because I don't have any medical experiment knowledge. So anyway, we are using these features for this uh, logistic regression. So I request all of you, if you are having the data set with you, then please have a look at this data set. and you have 8 input features, and you have finally the 9th column is giving you the class label. It's giving 1 or 0. 1 means diabetic, 0 means it's not diabetic. So the implementation steps are actually same as that we have done for that linear regression. So we have actually the whole data set. We actually extracted the inputs by extracting the first 8 columns of the data set, and that's actually done in exercise diabetes dataset dot ilog from 0 to 8 means extract the 8 columns and form a data frame out of that, and extract the 9th column. So that means 9th column, and that is your output value. Exact output values are in Y, and the input parameters or features are in the data frame X. And then what you are doing is, again, you will be doing, say this time I'll be using the training testing data set separately. So I'll be splitting the whole data into training data and the testing data with the test size of 0.3. With the test size of 0.3 means I'll be using testing data sets 30% of the whole, and 70% is used for the training. And then I'll be some print statement that's only for correcting some error. While I have implemented, there were some errors, and to actually try to go through these errors, I just printed some sort. It does not have any significance in the actual implementation, so please don't bother about that part, and just focus on the logistic regression fitting part, where we have function logistic regression with maximum iteration is equal to 1000. That I will explain if I get time. If we are not setting that parameter, there may happen that this is actually run into some error, come to some error, because there can be some maximum iterations for the runtime stack. It's actually not related with anything machine learning, but it's related with some experimental situation, experimental conditions with the Python programming. And you can set maximum iterations to, I think it's maximum to 8,000. I don't remember actually. And we'll be fitting the logistic regression model, and see that I'm fitting logistic regression model dot fit X train Y train. That means only using the 70% of the whole data, that is inputs X train and the corresponding Y train I am fitting. But later what I will be doing is that I will be predicting, or I will be doing the prediction for the test data. That means for whichever data I use, I actually created the model. I didn't use that data. The remaining data is used for checking the performance of the model. That is Y predict is equal to logistic regression model dot predict, and see the input that is given. It is X test. It's not X train. And then I'll be evaluating the performance of the model. See, after this, I'll be explaining how you are going to evaluate the performance of a classification model. There are some parameters for that. And let's say, first of all, let us see what is the output of this. Let's run this one. So this is, you can see a diagram. So actually, this is showing a matrix, namely confusion matrix. And this confusion matrix is actually for a binary classifier. It is a 2 by 2 matrix, which is giving the, or which is actually the graphical representation of what's actually the performance of your model. So on one side, or on the horizontal axis, what I'll be showing is the predicted labels. Predicted label means I have only 2 labels, not diabetic and diabetic. And on the vertical axis, I'll be writing the actual labels, diabetic and non-diabetic. So I can see 2 by 2 matrix here, and each element is actually a square here. And you can see some numbers there, 141, then 16, 35, 39. And see this 141. Actually, it corresponds to the indices. So you can take these labels, non-diabetic, diabetes, as the indices, and see what is the vertical index. It corresponds to the actual label, and what is the horizontal? It corresponds to the predicted label. Meaning is that, look at the first top row, left column. So non-diabetic is the row index and non-diabetic in the column index. Meaning is that in the whole data, training data, that is 141 samples, 141 samples are were actually not diabetic category, and your model is also predicting it as non-diabetic category. So that means the model is doing well for that 141 number of samples. That is top left. And look at the bottom right. There, 39 samples, 39 samples were actually diabetic category, and the model is also predicting it as diabetic. That means that 39 is also correct prediction. So out of that is 141 plus 39. This many number of samples, for this many number of samples, the prediction given by the model is that is exactly correct. But for the two other, that is top right and bottom left, they are incorrect predictions. Actually, it's specifying that 16 samples were actually not diabetic, but your model predicted it as diabetic. Similarly, 35 samples were actually diabetic, but your model predicted it as non-diabetic. So they are incorrect predictions. So your model is not 100% accurate. So the first part is called true positive, top left, called TP, true positive, that yellow section. And the bottom right is called true negative. That is, positive means here you can take it as non-diabetic. Negative means diabetic. So actually it's not diabetic, and the model is also predicting not diabetic. So it is truly positive. Model is actually is diabetic, and the model is predicting diabetic. It's truly negative. So you have TP and TN, and this is this, and we will explain this later. So let me just have a look. Just have a look. And here what I will be showing is that the accuracy of the model is only 77.92. So we will see what is the F1 score, recall, precision, etc. So just for your sake of knowledge, I am just saying that these are the parameters. That is accuracy, F1 score, recall, precision. These are the most commonly used parameters for expressing the performance of a classification model. So now let us come back to what are these parameters. Okay, so I'll be closing this window for a while, and I'll take the presentation again. Okay, the classification matrix here. Similarly, I've shown here. This is the class confusion matrix. And please recall our previous image. Here 1 stands for non-diabetic and 0 stands for diabetic. So 1 means class 1 or the non-diabetic class. 0 means that that is class 0 or diabetic class. True positive, that means actually it was class 1 and model is also predicting it as class 1. So true positive, that is how many in the whole data testing data set, how many were actually belonging to class 1. At the same time, they will be predicted by class 1 model also to be in class 1. How many such samples are correctly classified to be in the class 1 category? That number is called TP. And how many are correctly classified into class 0? That is called a true negative. And the other, that is actually it was class 1, but model predicted it as class 0. So that's called a false negative. False negative means negative is false. That means 0 is false. So in fact, it is positive. So false positive, that means model is predicting it as positive or class 1, but in fact, it's false. It's actually negative, which is actually the in class 0. So And based on this, so you will be having some values. Earlier we have 141 on the top left and 39, I think 39 or something like that in the bottom right portion, and some values in the other two cells. And based on these parameters, so we will be evaluating the model by means of 4 parameters called. One is the accuracy. Accuracy is, as you expect, out of the whole data sample, how many are actually correctly classified? That is, correctly classified are actually TP plus TN. That is the number of samples correctly classified divided by the total number of classifications. So that is TP plus TN plus FP plus FP. How many are correctly classified? That's accuracy. So the next thing is precision. Precision means, anyway, we have a positive class 1. Class 1 is there. And the model predicts some samples are actually class 1. But exactly all these samples may not be in class 1. So precision is actually giving you a measure that out of the whole predictions of class 1, that is, the model is predicting class 1 for a number of samples. Out of these predictions, how many are actually correct? How many are actually correct? So that is actually TP by TP plus FP. TP plus FP means it is the total number of predictions. It is the total number of predictions by the model to be in class 1. TP means exactly how many are in class 1. So TP by TP plus FP will be giving you the total number of samples which are correctly classified to be a class. Now, what about recall? Recall is sometimes called sensitivity. See, the model is actually, see, in the actual case, there may be a number of samples, say, which are actually positive. But out of those samples, the model, how many are actually the model is able to predict as truly positive? So you have some, assume you have some 200 samples, 200 samples in your data set, which are actually in class 1 or class positive class. But the model is able to predict only 100 number among these to be class 1, and the remaining 100 they are predicting as class 0. The meaning is that the model is having recall of 0.5 only. That means 100 by 100 plus 100. That is, so you will be having how many, that is out of the total number of uh, total positive cases, how many are actually model is able to predict. And there is another term is called the F1 score. So that is actually uh, a harmonic mean of precision and recall. I'll explain what is the reason why harmonic mean is taken. That also I will do. Harmonic mean is a term which is just like our AND function. AND function, AND function is taking two inputs, x1 and x2, and will give only the high value only when both are 1. Similarly, this harmonic mean is actually a function which will take two parameters, say x1 and x2, and the harmonic mean of x1 and x2 will be a high value only if x1 and x2 are high. And if one of them is low, then the harmonic mean is low. So by taking the harmonic mean of precision and recall, what we are trying is, we are in fact combining the precision and recall to a single value, which is actually a high value only if both precision and recall are high. If one of them is actually low, then the score will be low. Meaning is that one of either the precision is low or the recall is low. So it's only a term which is used to compare this, which is actually combine the precision and the recall types. And so these are the normal classification metrics. And so let us come back to our original implementation now. No. And you can see your model is having an accuracy of 0.779, means 77 point, that is almost 78% of the total predictions are correct. That's the meaning. Then it's having the recall of 0.5270 and the precision of 0.709. That means out of the whole samples which are actually in diabetic uh, category, which are not in the diabetic category, non-diabetic category, 70% are correctly classified. That's the mean. 70% are correctly classified. And the other one is also some weighted information. If I get time, I will explain. This support means actually the number of samples of class 0. That means there are 157 samples with the non-diabetic category in the test data and 74 samples with the diabetic category. So that is actually 157, and this accuracy, macro average, all these are actually some weighted terms. Actually, macro average means that just the weight of these column-wise average you are taking. And if I get time, I explain that because it takes some time, 10 minutes to explain how these values are actually calculated. Since we don't have that much of time, let me just discuss what is this. You go through the model and you see that you have only an accuracy of 77, the F1 score of 0.6, and recall of 0.5, and the precision of 0.7. And the F1 score, as you know, is actually the harmonic mean of 0.52 and 0.70 I told. And see, what all value you are getting is actually nearer to 0.52. See, this is 0.52 is nearer to 0.6 compared to 0.7. So since that means F1 score is always actually nearer to the least of the input values. And that's all about our linear regression, about the logistic regression model. Then let us come to the next model called the decision tree model. So actually, decision tree means actually we all know what is a tree structured data. Actually, so we will be having a data set. We want to classify the samples in this data set into discrete categories. How we will be doing that? We will be doing this with the help of a tree structure. And let us see what is actually classifying some data based on a tree. See, let us think about it. So see this tree is showing a decision tree where in the input set I have two features, that is about sky and windy. That's the atmosphere situation actually, sky and windy. Then our classification or the output is whether I should buy an umbrella or whether I should take an umbrella. Suppose I'm going for a journey, and based on the atmosphere situation, say atmosphere climate, whether I should take an umbrella. That's a aim. That is a category that we need. Buy an umbrella is one category. Don't buy is the second category. Only we have two classifications. So what it will do is, this is something which we normally do. It will first look into sky. What is this? Whether this is sunny or it's a rainy or it's a cloudy situation. So if it's sunny means we all know whether we don't need to buy umbrella. So just you can output no. You don't need to buy an umbrella. If it's rainy, then also you can say you should buy an umbrella. But if it's cloudy, then what you have to do is you should again check what is the windy situation, whether it is a windy situation or not. So if it's a windy situation, that means that, so we'll here it is classified as no, and if it is not windy, then we. So I have what is actually done here. Please see that I didn't calculate. Don't have any numeric parameters like alpha 0 alpha 1, alpha 2, etc. What I will be doing is that based on the features in the input, I'll be forming a hierarchical structure, and in the structure, each internal node is representing a test, whether it is what is the sky situation, whether what is the status. That is actually shown in the root node. And what is actually the leaf node showing? Leaf node showing is a result that is particular category. Will output a particular category. Here that is leftmost node is outputting the category no, and the rightmost leaf node outputting the category yes, like that. So each internal node is representing a test. And what is the test? The test is done based on the value of one of the feature. So let me explain this with another example. 1 minute. So I actually created some decision tree for the sake of explanation. It's something that I have drawn on my board. I'll share that. I think this is clear to I think everyone. Sir, is it visible now?
Yes, yes.
See, what I am showing here is a truth table, which has 3 inputs, Boolean inputs x1, x2, x3, and they one output y. And as you know, for 3 inputs, we have 8 possibilities, 0, 0, 0 to 1, 1, 1. And you treat these x1, x2, x3 as your features. And these samples are actually shown 1, 2, they are numbered as 1, 2, 3, 4 in black color. And the output y I have shown for only for the first 2 inputs, assume your output is 0. And so here we have only 2 categories. Your category is your output. So y is equal to 0 means that first 2 inputs belonging to the 0 category, then remaining 6 will belong to the second category, that is 1 category. So you are going to design a decision tree here. But by designing, so what do you mean by designing a decision tree? Meaning is that you form a tree like this, which can be used to predict the output, what is the y value for a particular input. And you see that when you design a decision tree, you are not calculating any alpha 0. You are not calculating alpha 1, alpha 2, just as you are doing in logistic regression or linear regression. And such a model where we are not calculating these parameters, any numerical parameters associated with this model. Such models are sometimes called non-parametric model. Decision tree is one of the best examples. See, I have shown one clearly illustrated how this works. So in the root node, what I will be showing is that I'll be testing. I have 8 samples there, 1, 2, 3, 4, 5, 6. That is shown in the as an 8 tuple, and with these red dots on the top of these labels, indicating that 1 and 2 are belonging to class 0, and the blue dots in the tree, that is indicating that the remaining 6 are in the class 1 category. They are the output y is 1 for those inputs. And for 1 and 2 are actually the leftmost labels given to the data sets. You can see that on this data set itself. Now, what I will be doing is that I'll be just performing at the root node a test based on the feature x3. I'll be choosing as x3 as the feature for testing at the root node. So I have 2 values for x3, one value is 0 and another value is 1. So accordingly, I have 2 branches. One branch corresponds to the case where x3 is equal to 1, and the other branch corresponds to the branch where x3 equal to 0. And for x3 equal to, there are, see, out of the 8 samples, x3 equal to 1 is for 4 samples. That is 2, 4, 6, and 8. That is shown in the left node of the root, left child of the root. And the remaining 4, 1, 3, 5, and 7, they are in the right. They are actually having x3 equal to 0. See that? Again, you look at the data set in the left child and right child. It includes class 0 type or 0 0 y inputs and 1 y inputs. There also that situation. So you cannot say that the output is that means for sample 2 still the output is 0, for other samples output is 1. Therefore what I'll be doing is that I'll be splitting that into that data, the leftmost child data, in based on the second feature. Say maybe I have chosen as x2 as the feature, x2. So x2 is used as the test for the left child of the root node. So accordingly, I have two branches. Since I have x2 values, two values for x2, x2 was 1 and x2 was 0. So at the left child of the root node, x2 equal to 1, meaning is that at this left child we have only four data samples, 2, 4, 6, and 8. And out of these 4, how many are having x2 equal to 1? 4 and 8. You can, when you go through the table, you can see that 4 and 8 will be having your x2 will be equal to 1. And see this 4 and 8. 4 and 8 are now actually in the same class, same category of y. Both are having y equal to 1. So that time, when your inputs associated with a particular node are all in one particular category, you can stop there, because at that time you reached a case where all the samples in that particular associated with that node are uniform. So what is the category corresponding to this? Their category is actually 1. So you take that as a leaf node and output a value 1 there. Output a value 1 there. So at a later point of time, if you can use this for, I will explain that later. Instead, you consider the right path, x2 equal to 0. See, of the left child, right path, x2 equal to 0. Again, say 4, 8 is there are 2, 6. And see, that data is not uniform. 2 is category 0 and 6 is category 1. So you will have to again do the classification based on the third feature x1. So you anyway use the x3, you use the x2, and the remaining feature is x1. So you will be using the categorization based on x1. x1 equal to 1 corresponds to one path, x1 equal to 0 corresponds to the next path. And the 2 will be in the, that is only for 2 x1 is equal to 1, and only for x1 equal to 0. I think I reversed it. So anyway, one of this is having I've written wrongly. Having in one left path and one is data sample is associated with the right path. And see, there you can output the category, because when there is only one sample associated with a particular leaf node, with a particular node, then there is nothing to do more, because at that time you don't have more samples. You can output the category of that particular node, particular sample. That is what is done here. And the similar thing is done for this remaining part of the tree roots. So at a later point of time, suppose I am going to give 1, 1, 1 as the input. If somebody asks you what is the output of this particular Boolean circuit when the input is a 1, 1, 1. So what it will do is that it will take the value of x3 first. x3 equal to 1. x3 equal to 1 means the left child path of the root node. Then it will take x2 value. x2 is also 1. x2 is also 1 means the leftmost path of the left child, where you will be having output value 1. So the model is correctly predicting your output. This is one decision tree. You may think that this is the only possible decision tree. No, there is no strict rule that you should first check x3 first. There is no strict rule that you should check x2 first. And there can be accordingly several decision trees possible. I will also show another decision tree. So you see that this decision tree is having 1, 2 is having a depth or height of 3. Now you look at this decision tree. The same thing is also done here. Same thing is also done here. But instead of doing a checking with x3 at the root node, at first I will be doing a checking with x1 here. When I do a checking with x1 itself, what you can see See, x1 equal to 1 is only for the data for 5, 6, 7, and 8. So that test corresponds to set of samples whose category is the same. So that is the left node of the root node, left child of the root node is now associated with samples of uniform type. So that can be treated as a leaf node which will output the category 1. And accordingly, you can see the right node x1 equal to 0, where you will be having 1, 2, 3, 4, where 1, 2 corresponds to 1, 2 corresponds to category 0 and 3, 4 corresponds to category 1. I forgot to put the dots there for the right child. And then I'll be just doing a test for with the x2. And with x2 equal to 1, I'll be getting 3, 4 on one side and 1, 2 on other side. And that will complete this. And you see, you are not using x3 at all here. So what is the conclusion is x3 was actually a useless feature there for the classification. So you can see that for the same data, I will be able to create different types of different decision trees. And this decision tree is having a height of 2 and the other one is having a height of 3. And better you design decision trees with lesser height, otherwise it will become there will be a situation where the tree is overfitting. It will lead to an overfitting situation. So anyway, so there may be a natural thought, which tree will be the best? So given a particular data, which is the test to be done first, which is the feature to be tested first, to be tested next. And that is actually designing a decision tree based for a given data. And there are algorithms for doing this. And these algorithms, there are ID3 decision tree algorithm is there, and the CART algorithm is there, classification and regression tree algorithm. These are the two famous algorithms commonly used for designing these decision trees, and they will be using some techniques, some mathematical measures called impurity measures like entropy, Gini index, information gain, etc., to determine which features are to be chosen in which priority order. And these parameters are actually strong enough to give the relevance of the parameters in determining the output. So I don't discuss this because it's very detailed, lengthy algorithm, it's a recursive algorithm both. And the point is that for a given data, there may be several decision trees, and finding the optimum one is a task, and that is done using some algorithm called ID3 decision tree or CART decision tree algorithms. Now I'll be coming across the implementation of this. The second code segment that is I have taken here, it's for the implementation of the decision trees. The only thing is same for the PIMA dataset itself. I'll be using for the diabetic prediction instead of logistic regression. Now I'm using a decision tree model where diabetic is one category, not diabetic is the second category. I use the same code as for the training test dataset, only the fitting the regression model, fitting the decision tree model. Say in that there are I forgot to remove that comment. Actually fit the not the fit the logistic regression model, it's actually fit the decision tree model. So 2 lines. Decision tree model is equal to decision tree classifier max depth equal to 5 means in this particular example, I allow the tree depth to be only up to 5. I don't allow the tree depth to be more than 5. That means only 5 features can be chosen. That is, tree depth is more than 5 means I cannot actually make it to display here. So you can see when when the tree depth is more than 5, it's very difficult for me to for this to display the tree here. That's why I have chosen as max depth. You can choose up to max depth equal to 3, 4, 5, 6, 7, up to 8 you can choose. And then I'll be fitting the model using the training data X train and the corresponding Y train. and I'll be evaluating the model for the test data, yeah, as in the previous case. And I'll be taking the confusion metrics, then printing the accuracies, F1 score, recall, all those things for this. This is this function, and this is the tree actually. This tree is actually created in this Python by means of the cart algorithm. In the cart decision tree algorithm, that is always you will be getting a binary tree as a decision tree. And cart algorithm is actually a better algorithm compared to ID tree, because cart algorithm can be used to design decision trees for regression also. And I am not able to explain the actual reasoning behind this, why they have chosen this glucose values, then age value. First, they have done the test with the glucose feature. What is the whether the glucose value that is less than or equal to 144.5. That is true. Yes is for one branch and no is for the other branch. Then they will be checking whether the age of the person is less than or equal to 28.5. Yes for one branch. Like that, they'll be doing it for five up to 5 levels. So that is actually shown here. And because of difficulty in displaying this, actually showing here. And this is the confusion matrix now. Same thing. And in this case, this is your performance. This is the performance of the model. Accuracy is actually not that much. Previously, it was 77. Now this model is actually up to 73 point actually. And the F1 score is actually 0.56. Previously, it was 0.6. Recall was 0.54. Recall was previously it was 0.52, but now recall is improved. But precision previously it was 0.70, but now it is only 0.59. That means out of the compared to the previous model, the non-diabetic prediction is not as accurate in this one. That is, non-diabetic category prediction is not that much good in comparison to the same in the previous model. That is the logistic regression. This is what is actually shown here. And you see your confusion matrix also, you can see that is a situation. I think so this is the confusion matrix. Previously, 141 samples were able to be predicted non-diabetic category. Out of 231, 141 were able to be correctly predicted, but here only 130 is correctly predicted. So comparatively less performance compared to the logistic regression. And that's about our decision tree model. And let me come to the support vector machine model. Christy, are you here? Hello.
Yes, sir.
Okay, you are here. I'm going to explain this. So in this session, what we'll be having is a game demonstration of this model. Actually, I have invited one of my students, Ms. Christy Teresa Chapo. She had implemented a project, namely playthrough machine learning. It's actually a game to teach machine learning model. Not a simple game, it's actually a game which is used for teaching machine learning models. And we have actually created 4 games, one to teach the k nearest neighbor classifier, one for decision tree, one for support vector machine, and one for neural network. And I'll be just giving a demonstration of support vector machines using this. And because I think it's very good to explain the notion of margin with this game. So let me come across the support vector machine. What is actually support vector machine? Support vector machine is like this. It's also actually a binary classifier. Say, you may imagine a situation like this. We are all teachers. Say, assume we are teaching in a class where the students are diverse skills. That means there are students with excellent academic skills, and there are people who are lazy. That means who don't have that much of academic skills. So basically, we have two categories: excellent or studious or non-studious type. And when we are teaching in such a class, what we'll having is we'll be facing a difficulty that on which community should we focus? If we focus on the excellent or studious community, then the other team is going to lose because they don't get anything. Because we are teaching from such a level, we are maintaining such a level of standard in our lecturing, so that the other people will not be able to grasp anything which we deliver in the class. But if you focus on that lazy people category, the thing is that the other people may feel that the class is a very useless class, because most of the things the teacher is explaining in the class is actually very fundamental. So no need of attending that class. So therefore, what we should do is we should keep some stand in between this, some better position in between this. That's the usual thing that we teachers normally do in the diverse community of students. So I'll tell you a better way for what teachers normally do. Where to place our stand. For that, my idea is you should not focus on the whole students, but you should focus on only some 2, 3, 4 students. Only by focusing on these students, you can actually pick up a better position. You can pick up a better position which is suitable for both the community. What is that position? So for that, you should choose the lazy people among the excellent category and the excellent people in the lazy category. You should take the lazy people in the excellent category and the excellent people in the lazy category. So you will be having some 2, 3 lazy people in the excellent category. You will be having some 2, 3 excellent people in the lazy, and the others for the other category, and leave all other students. Forget about all the students, and you pick up a position with respect to these students, only with respect to these students. Please don't bother about the remaining students. So maybe your class is having 100 students, but now you are in a position to pick up a stand which is best suited and is based on only some 4 to 5 students. And you see that position is suited, that position is working best for the whole class itself. And this is the idea of support vector machine, where we will be choosing the lazy among the excellent and the excellent among the lazy. Those people, those students are called the support vectors. Support vectors. And only based on the support vectors, we will be fitting a boundary that is actually shown in the red line, in the red line in the figure. And the purple color, that maybe you may treat it as excellent students, and the green category maybe the lazy students. And I have shown 2 lines on either side of the red line, and one line is passing through the lazy students in the excellent category, and the bottom line is passing through the excellent student in the lazy category. And you keep a position in between this. That's all. Why do you bother about other things? That is the idea behind support vector machine. Then naturally a question, where to fix? See, so how will you place that red line? So that is to correctly place the red line. That is the actual task of designing a support vector machine. And for that, what we'll be calling is, we'll be using a notion called margin. And here I have marked as gap. Now I'll be explaining that notion of margin. This is my video. See, can you say, I'll stop this presentation. Can you present that case?
Yes, sir.
There is some narration sheet, so please don't bother about it. So you may skip, Christy, you may skip the narration because we don't have the sheet. Okay. See. No, please come back to that previous. Okay, please stop here. See this, here are the data. See, on one side you have the blue type, and on the other side you have yellow type. So maybe blue type belong to category 1, like this yellow type belong to category 2. You want to fit a particular line boundary or linear boundary, this for classifying these two. That means on the one side of the line, one category lies, on the other side you on the other category lies. Okay, you want to where you should fit the line. First of all, you should pick the people, or which I call as support vectors. So proceed. So she had called this one person as support vector, then the next person as support. So you see that the two vectors I have shown, and see, in between these students, I have to place a line. That line is actually support vector. And then you may think that, okay, just place that line in the middle. So that will be the okay. And you see the distance between the two lines, you can see it is 254.247 now. But if you just place it in the middle, that may not be the best line or the best boundary that you can set. So that I will be explaining with a demonstration. Christy, can you rotate? So please see. So, see, when you rotate this line, you see that the perpendicular distance among them between the two support vectors, they are actually changing. So now it is 249, 247, 246, actually decreasing. But on the other side, if you increase, try to rotate, now see, it is 251 now, just 252 now. Now just rotate towards the left. So please don't see, just focus on the vicinity of 250, 251 on the 50. Please don't go ahead too fast. Please keep it in the vicinity of 250, 251, and only you rotate when I say. Okay, 250. Just rotate towards the right, 251, 252, then 253. See that you will be seeing that the 254 is now, then 255 now. That means it is not always the centric line. The center line is the best fit. And use now in this direction, so you will be placing a line in the middle in the same direction. And okay, you may proceed further. Now the distance between them is 255.217. On in this inclination, I will be placing a line at the middle. Please, next. Now this is the line, which is actually, this is the separating line, and which is actually placed in between the two lines. That is nearly the two. I have drawn two boundaries which are far away with a distance of 255, and on the center in the same inclination, I have kept this line. And in which inclination is to be this line is placed. And this is for the case where you will be having only two features. See, the students are actually in the 2 dimension. When you are having the features in the 3 dimension, instead of a line, you are actually placing a plane here. In the fourth dimension, you are placing a hyperplane there. So always we are placing a linear boundary with the maximum margin. That is the target objective in the case of a support vector machine design. I think the idea of design of support vector machine is clear for everyone. And advantage of this support vector machine is that, say, please think about our linear regression model. So, okay, you may stop this. Think about the linear regression model. In the linear regression model, if some points, say, we have only some, say, 10 points, say 9 points are actually in the vicinity of some particular values, but the 10th point is actually far away from the 9 points. That point is called an outlier. And that outlier point will make too much issues in our model, because when we take that SSE value, that model, that extremely high difference will make too much, will actually have too much role in determining the parameters of the model. Therefore, outlier is actually a problem in the case of this linear regression model. But SVM does not have such model, because out of the 74 students, it is actually only designing using some 2-3 people, and the rest are actually all were left. So this outlier, it is actually not suffering the issues of outliers in the case of SVM model. And explaining the theory behind this SVM is not that much easy. It requires an in-depth knowledge of convex optimization as well as linear algebra. So in particular, we need to know about what are called Lagrangian multipliers in optimization theory. And if somebody wants to have a close look into the exact theory behind this, you may actually proceed up to one mathematical formulation of this SVM, that's called the primal formulation. And beyond that, you should have some knowledge about what are called linear Lagrangian multipliers, and how we will be forming the dual formulation from a primal mathematical program. So therefore, SVM is normally considered to be difficult in explanation. And now we will come across our SVM implementation. This is a third code segment is showing the SVM implementation. Same as done the previous scikit-learn packages, everything is the same. Pandas, NumPy, everything is the same. Matplotlib, there is no difference at all. And the only difference is in this model fitting, where I'll be using this SVM that is model by means of a function called SVC, and the parameter I cannot as X linear kernel. Some kernelization is actually a trick in this SVM for designing SVM for non-linearly separable data. That means, say, in the last case, what we have seen is the two categories of data can be separated by means of a linear boundary, but in practical situations that may not be the case. So in that case, we will be doing some procedure which we call as the kernelization, kernel tricks. And there are several kernels available. One kernel is the linear kernel. There are other kernels also. I here use a kernel as linear, and the other kernels also are there. And you will be fitting that SVM model here. And with the training data X train and Y train, SVM model dot fit X train with Y train, and we will be evaluating again with the X test, and you will be getting the class labels for this particular, which category of people having diabetic and which are having non-diabetic. And we will be again doing the same thing, measuring the performance using the same performance measures, confusion metric, everything. And now what you can see, I'll be running, see the category, you will be obtaining an accuracy of 78.35, that means 0.78, and the F1 score of 0.61, recall of 0.54, and the precision of 0.71. Something a little bit improvement over the logistic regression, but compared to the decision tree, it is better. And again, 141 the non-diabetic samples are correctly predicted here, and in the confusion matrix, and the 40 diabetic category are correctly predicted here. And so after we see, for the same data set, I created different models. After creating, say, I created a decision tree model, a linear logistic regression model, and an SVM model, and you can compare the model performance, which one is doing the best. And in fact, there are some methods to combine these models. Some techniques called the ensembling is also there. So we don't have the time to explain why this ensembling is there. So that's all about our SVM discussion. Now, I have already committed to explain the reason why we will be using some 1 by 1 plus e power minus x in case of logistic regression. So let me come back to that part, and say within 5 minutes I'll be explaining what is the reason why, instead of using some probability of the output equal to 1 as alpha 0 plus alpha 1 x, why do we use such a complex formula? I'll just write it here. This is for only for decision trees. Just close it. Take another. So you will be having your data as x1, parameters as x1, x2, x3, etc. xn. What you have seen is that you will be predicting the probability that y equal to what is the probability that the output for this input data is, or the category for this particular data is 1, given x2, etc. xn. We all mentioned that is actually 1 by 1 plus e power minus alpha 0 plus alpha 1 x1 plus alpha 2 x2 plus etc. alpha. Why such a complex? Actually, let us think about the situation where we want to predict this probability with such an expression, like we have done in the case of linear regression. Assume this probability can be estimated by means of an expression by a linear combination of the inputs. Like, let us see what will happen. See, anyway, the left-hand side is actually a probability. Its value is supposed to be in the range 0 to 1. Left-hand side, since it's a probability. But you look at the right-hand side. See, your x1, x2, x3 values are actually any real numbers possible, negative as well as positive. So you don't have any restrictions over them because they are user inputs. So with that, the right-hand side you cannot limit in between 0 to 1. Rather, it can range in the infinity to minus infinity to plus infinity. Because your x1 feature may be 10,000, x2 feature may be 1 lakh, x3 feature may be 0.001, x4 may be minus 20,000, like that. How we can? Therefore, this is not possible. You cannot measure the probability as a linear function of a linear combination of the features. Is not. Therefore, we should. So you don't have any restriction over this because these are user inputs. But how are you going to map or make these two ranges or to be identical. For that, what I am going to do is, let me take this parameter as some say p, small p. So what is this? It is the probability that the corresponding input is belonging to category 1. I'm going to divide this probability by 1 minus p. So this term, what is this? This is nothing but the probability that the particular input is in class 1 divided by the probability that the input is in class 0. Because if the input is not in class 1, then it is in class 0. Because we have only two categories. If p is the probability for class 1, then 1 minus p is for class 1. So here what I am done is I just divided the probability of one event by the probability of occurrence of one event by the probability of not occurring that event. Probability of occurring and particular event. Here the event is y equal to 1 divided by the probability of not occurring. And that term is probability in theory. Probability theory, it is called the odd of that event. Odd. It is called the odd. So now odd of an event means the probability of occurring that event divided by probability of not occurring that event. Now, if you take, and instead of this probability to be this alpha 0 plus alpha 1 2 etc., in probability to be this alpha 0 plus alpha 1 x1 to alpha n xn, you take p by 1 minus p to be this one. You take p by 1 minus p to be alpha 0 plus alpha 1. Okay, previously it was 0 to 1. It was alpha 1 x1 plus etc. alpha n x. Now see, still here it is in minus infinity to plus infinity range. Here, when see the least value of p, since it's a probability it is 0, so 0 by 1 minus 0. So the least value is actually 0. But the highest value for p is 1. Therefore, 1 by 1 minus 1, that is 1 by 0. So now the range actually is matching with the right-hand side limit. See, on either side, LHS as well as the right side, as the right-hand side, see that the intervals for the LHS function and the LHS function, the upper limit is the same. Both are infinity. But still there is an issue. So this is the odd of, called odd. It's a term that is normally used in probability theory. Now, the upper limit is the same, but still the left-hand side is having the lower limit 0, but in the right side of the linear combination, the lower limit is minus infinity. So we should be able to match that also. Therefore, what I have to do is I'll be taking the logarithm of this. The thing is that logarithm of 0 can be taken to be minus infinity. What is ln 0? ln 0 means log e, which is the power you should apply to 2.73 to get the value 0, which is the power. So you should apply 2.73, power minus infinity is 0, because 2.73 higher powers will be giving infinitely range. It is increasing. So you give only negative values. Ultimately, when you give it is minus infinity, you will be getting 0 value. So that means logarithm of 0, ln of 0 is minus infinity. Therefore, what you will do is that you take ln of p, instead of taking odd as this linear combination, you take the logarithm of the odd as the linear combination. ln of p divided by 1 minus p to take as alpha 0 plus alpha 1 x1 plus etc. alpha n x. Now the range is matching, because when you give p is equal to 0, log n of 0 is minus infinity. When you give p is equal to 1, log of 1 by 1 minus 1, log of infinity is infinity. So both the ranges now match. Log. Now ln p by 1 minus p is this one. Therefore, what is p? P is therefore e power alpha 0 no, p by 1 minus p. You take ln of p by 1 minus p is this one. Therefore, p by 1 minus p equal to e power alpha 0 plus alpha 1 x1 plus etc. alpha xn. And you can simplify this to p is equal to e power alpha 0 plus alpha 1 x1 plus etc. alpha n xn minus p into e power alpha 0 plus alpha 1 x1 plus etc. alpha n xn. You take p terms towards the left. So p into 1 plus e power alpha 0 plus alpha 1 x1 plus etc. alpha n xn to be equal to e power alpha 0 plus alpha n xn. Therefore, p is equal to e power alpha 0 plus alpha 1 x1 plus etc. up to alpha n xn divided by 1 plus e power alpha 0 plus alpha n xn. You divide both numerator and denominator by the numerator itself. So you will be getting 1 by, now this term is same as the numerator. So from there also you will get 1. And this term 1 by e power of this. So that is nothing but e power minus of alpha 0 plus alpha 1. And this is how you obtain this. Yes, and p was actually an abbreviation. It's a shorthand notation for probability of y equal to. And this is how you obtain that expression. Initially, we were happy if we were able to take the probability as just as linear combination of the inputs, but unfortunately, we don't have that option. So we were forced to take this. And this, what I have taken is, I take the odd logarithm of the odd function. Odd was p by 1 minus p. And I have taken the logarithm of the odd as the linear combination of the inputs. And this logarithm of the odd is called a logit function, logit. And since the logit function is used, this regression is called a logistic regression. That is the point that I am to explain. And that's all about my presentation. If you have any doubts, you may please ask.
Thank you, Anil, sir. Is there any question from the side of the participant? I think there is no more question from the side of the participant. So it was in fact again a wonderful session by Professor Anil Kumar. He started with the supervised learning technique, basically the logistic regression, and then he moved to the decision tree, and finally he showed a demo of the support vector machine algorithm. And at last he explained why the name logistic regression. And there was a presentation by Christy Teresa Chaco. She was a student of our institution, the Govt Institute of Technology, and she, under the guidance of Professor Anil Kumar, along with her teammates, they have developed a wonderful project of explaining how these kind of machine learning algorithms are working, and that is in fact a step towards a gamified way of knowing things. Uh, so once again, I would like to say that Professor Anil Kumar has the capability to explain complicated things in a simple way, and I think for the participants, it has been a good session, and their knowledge in machine learning, especially in the case of supervised learning, has been taken to the next level. And from the side of Department of Computer Science and Engineering, Rajiv Gandhi Institute of Technology, once again, I would like to extend our sincere thanks to Professor Anil Kumar. Thank you, sir.
Thank you, sir. Once again, I wish best wishes for all of you, and thank you for your cooperation. Okay, sir, I'm leaving.
Thank you, sir. Thank you.
And, I think we can take a break for maybe 2 minutes. Uh, and after that, we will start the next session. We know that it is really tiresome for uh, teachers, especially teachers, to listen to online lecture for such a long time. And to the participants, once again, thank you very much for your cooperation. And we will break for 2 minutes, and after that, we will start our next session. Please
Okay, sir.
don't leave. Uh, we will continue with the same meeting.